All right. In a minute here, I'm going to draw some pictures on my iPad and have them go on the screen, but I'm having some technical difficulties. So while I fiddle with that, are there any questions on, we're up to Chapter 4 now, linked lists. No questions? Who wants to start us off by describing at a very high level what a linked list is? Right. I don't know what's going on here. It worked yesterday when I tested it. Well, I have no idea why it's not working, so we'll go with the old-fashioned way. Right. So let's hope these pens work. With arrays, we have sure. Can anyone see that? Just barely. I don't think the yellow is going to be much better. Yeah. Okay, so in an array, we have a bunch of stuff. And things are stored one right after the other. And when we create an array, we say, this is how many pieces we're going to have in the array, and we're pretty much limited to that. If we're going to need more pieces, we need to, like we saw Tuesday, destroy the old array, make a new array with all the same data in it. Hopefully that's bigger. That can get kind of irritating. And so that's the main reason we have data structures, and one in particular is this idea of the linked list. Linked lists are not very good for random access. They're very convenient if you want to put things at one end or the other end, because that's what you keep track of. Then everything else is just linked to each other. And it ends up looking something like this. We have a data piece here, and some sort of pointer that points to the next element. And eventually we get a chain. Each piece of the chain looks something like this. So we can get another piece of data. And so on and so forth. And there's nothing special about the one all the way at the end. It's exactly the same type of node or link. It just doesn't point to anything. So its next item is null. And we can describe this in terms of code that looks something like call it a link. What do we want to store in this linked list? The book looks like it likes using ints. So we'll use ints. So int data, and then a reference variable called next that is of type link. So it points to another one of these guys. So using those, we can construct a chain. But we need some way to refer to this particular item, or in theory, any of them. But this is a good starting place, because from here, we can access everything else just by following the chain from next node to next node to next node, and so on. So we can call this something like head. And if we really want to, we can point to the last item and call it tail. That will make it very easy to add things to the end of this linked list. We just ask the tail, or figure out what tail points to, get that object, create a new link, and say tails next should point to this new link. And then we move tail to point to this new link. So in terms of this picture, it would look something like this. We create a new link. We want to draw it sideways. That points to nowhere. Put a new piece of data in it. Make this link point here. And then, I think I lost the T here. Get it. And then change tail to point to this new link. What other operations do we want to be able to do on this? Inserting a new link in the middle is kind of funky. So we create a new link, points to nowhere, has a new piece of data in it. Let's say it's going to go in between this link and this link. We need to do two things, right? Make this pointer point to this link, and make this pointer point to that link. So once we know something that refers to this link, we can say that its next should point to this new link, which gets rid of this piece. And hopefully while we're doing this, we hold on to what its next was, where it pointed to. And then we can assign that to this pointer here. What else might it be useful to do? Remove nodes. We can do that too. We determine that we want to remove this node. Its next has to be pointed to by the one prior to it. So we need to, should probably start by holding on to this temporarily, then making this guy point down here, get rid of this guy, and success. Adding something to the beginning is just like adding something to the middle, except instead of the pointer pointing to the new node being a next from a link, we just change where head is pointing to. So I get rid of my array. Create a new link, make it point to this, and then change head so that it points here. Questions? So what are some upsides and downsides to using linked lists? I assume the book talks about upsides and downsides of linked lists. So upsides of linked lists. How are linked lists in some ways better than arrays? I think I already answered this question at the beginning. That's a big one. I can add things to this linked list. I'm not limited. Well, I am eventually, but not in the same way that I'm limited by an array. Right? An array of size 6, I can only store 6 things in it. A linked list doesn't have a fixed size. On the flip side, computing the size of the linked list is kind of irritating. I have to count how many links it takes in order to get to a next that points to nothing. Inserting into a known place in a linked list is pretty quick. I just have to change 2 references, and that's it. In an array, I'd have to shift an entire piece of the array to over one way or the other. That's assuming I want to keep everything in order. And this does have inherent order. This is the first element, and that's the last element. In this case, the 5th. But there are also downsides. If I want to go to a specific element, let's say the 4th element, I can't just access the 4th element directly like I would with an array. I can't say linked list index 3. I have to say, let's go to the head. Okay, that's the first element. Move on to the next one. That's the second element. Next one, that's the third element. Next one, that's the fourth element. And then I get there. So getting to a specific element is kind of slow. If I already have the desired node, everything else is pretty quick, but getting to that node is pretty slow. Let's see, what else? Any other upsides or downsides that I forgot about? Did anyone not read Chapter 4? You should get the book. Are there? Do you know if there are any in the bookstore?
My mom was purchasing it in the bookstore, and she wanted to purchase it online.
Okay.
In a bad position.
There is an electronic version of this book. I don't know if it's available for download for free. And even if I did, I probably wouldn't be able to say one way or the other. Alright, so that pretty much covers the first section. That's what a linked list is and how it works. Things to be careful about in a linked list, because we're dealing a lot with references, pointers, and especially because we're actually expecting that one will be null, is the null pointer exception. One slight mess up, and it's very easy to either end up losing half your linked list or getting a null pointer exception. Luckily, people have written linked lists over and over and over again, so we know all of the issues that we're going to run into. Let's see, what else? I like this, page 197. Earlier in the book, he talks about testing. And there's this notion of boundary cases. The cases that we don't really think about that are kind of special cases that tend to bite us every once in a while. On page 197, he talks about forgetting to test the empty list. This is, I guess, the linked list analog of the zero condition. Lots of times you test methods and you expect something that's not zero, and when you give them zero, they break horribly. When you're dealing with linked lists, one of the things that you kind of accidentally ignore is what happens if your linked list has no elements in it. If you automatically assume that head points to something. When you create a new linked list that is completely empty, head doesn't point to anything. But if you write the algorithms correctly, we'll do that in the second half, or possibly the first half, since the iPad thing didn't work. We'll make sure those things work. Let's see. What else do we want to do? Okay, so if you're using a linked list just as a collection of data, really the only two operations you have are add and remove. And you can do add as just add it to the end, and remove as look through the list starting at the beginning, and when you find it, just take it out. That's one way of doing it, but sometimes we want to keep things sorted. So if we want our ints in this particular linked list to always be sorted, we have to do some other clever things when we're adding. When we have a completely empty linked list, it is by definition sorted. An empty list of anything is by definition sorted, as is a collection of one element. It can't possibly not be sorted. So when we add an element, when we're going from 0 elements to 1 element, it really doesn't matter where we put it, mainly because there's only one place we can put it, and that doesn't change the fact that it's still sorted. So adding an element and attaching it to head, we have a sorted list of size 1. If we want to add another element and it is, let's say, we want to sort less than to greater than, or smaller to larger. And let's actually put some numbers in here. Let's say our first element is 4, and our new element is 3. We go through the list until we find an element that's larger. In this case, with a linked list of size 1, this is the first element that's larger. We still hold on to the last pointer. And once we see that this node is greater, we know that we have to add this new element after the head, basically at the head. It becomes our new head. So we put a 3 here. We need 3 to point to that, and we need head to point to 3. Let's say we're adding 7 to this list. 3 is not larger than 7. 4 is not larger than 7. And at this point, that's the extent of our linked list. So we've hit the null, so we know that's the only place it can go. Let's add 6. Do you want to explain what happens when we try to add 6? Right, but just describe the whole process. Start at head. Yes, but we don't have access to any of these elements. We just have access to head, which then points to this element and so on and so forth. So if we start at head, the next element is 3. 3 is what element are we adding? 6. 3 is not larger than 6, right? So what do we do from there? Okay. Okay. Okay, so what do I have to do? So there's my 6 element. 6 has to point to this one, and then I change 4 to point to 6. Let's change it slightly now, and let's now say I want to search for 6. I want to do 2 things. First, see if 6 is in my linked list, and secondly, find out where it is. Let's say both the number of the element number that it is and get a reference to it. Return that particular node. So the only option we have available to us is start at the head, look at 3. 3 is not 6. Go on to the next one. 4 is not 6. Go on to the next one. 6 is 6. So if I've been maintaining a counter, I would have gotten 1, 2, 3. It's the third element, and I can just return a reference to that that node. Let's look for 8. 8 is clearly not in the list. We look at 3. 3 is not 8. Go on to the next one. 4 is not 8. Go on to the next one. 6 is not 8. 7 is not 8. And at this point, we have a null pointer. So we should stop trying to go on to the next one, otherwise we'll get a null pointer exception, and that's bad. But at this point we can say there's nothing else in the list, we haven't found 8, 8 must not be in the list. Valid conclusion. Any questions on the mechanics of linked lists? So now we can talk about variations of linked lists. There's a specific type of linked list called a doubly linked list, which is kind of a bidirectional linked list. The term head and tail don't really have any meaning anymore. And the difference is that now we have pointers going the other direction as well. So tail still points over here. And we can traverse the linked list starting at the head and going this way. We can also start at the tail and go this way. So in essence, we have 2 heads. We don't really have a head and a tail. If we do, it's really an arbitrary distinction. And the benefits to that, it's really that you can go both directions. If you start at a node in the middle, for instance, you can figure out whether it's closer to the head or closer to the tail. You can find out what the node previous actually is without having to start at the head. Given a node, you can figure out, oh, this is the node before me. In practice, I don't think I've ever used a doubly linked list. The Java array list might use one, as it's underneath. No, array list uses an array. So, note about the Java collection classes. Most of them are named in the form of 2 words that are smashed together. We have array list. The book mentions hash map earlier. And the way they're named is the underlying data store is named first, and then the interface that it implements is listed second. So array list is a list that uses an array to store its stuff. Hash map is a map, which is a key value parent, or a set of key value parents, and it uses a hash function to organize how it's going to store all that stuff. And there are a bunch of others, but those are the 2 most commonly used varieties. So let's make a linked list. no public class linked list. This is going to be interactive. Feel free to shout out what I should type next at any point while I'm typing. If you get ahead of me while I'm typing, that's fine. I'll just type faster. In theory, the first thing that I type should be comments, but we'll leave those out. So in order to have a linked list, I need a node, right? Up here I called it a link. Let's keep that the same. I'm going to show you something new in Java that you probably haven't seen before. Java can have something called nested classes. I won't explain when they're useful. My feeling is that if a nested class is the right thing to do, it just kind of feels like the right thing to do. In this class, in this situation, having a nested class seems like the right thing to do. A link doesn't really have any meaning outside of a linked list, so it really doesn't need to be its own class outside of that. And to be quite honest, it really doesn't need to be visible outside this class either. So I can declare a private class called link, and because it's private to this class, and I know this is a scary thought, but I trust myself when I'm writing the linked list class. I'm not going to make the link class follow all the rules that we normally follow when we write an object, when we write a class. So my instance variables are going to be public. They will not be private. I will not be writing properties, accessors, and mutators for them, and all those helper functions or helper methods. There probably aren't going to be any that are necessary. So I'm basically going to implement what I wrote here, and we'll handle ints. So int data and link next. So a linked list, it's probably a good thing to store. Well, it's definitely a good thing to store the head, and it's also a good thing to store the tail. Let's also create a constructor, and this should initialize the linked list. Yes. We'll see. Maybe. I think most of what I'm going to type is actually right out of the book. So, at least the book provides an implementation of a linked list that will be remarkably similar to what I'm going to type. A linked list is pretty much a linked list is a linked list is a linked list. There's not much variation. It looks slightly different in different languages, but it's all the same thing. And like I mentioned on Tuesday, last class, most methods that are involved in putting together data structures have very short implementations. So, what should I do for my initialization? I create an empty linked list. What do I need to do? I'm sorry? I still can't hear you. If I'm creating an empty linked list, I don't have any data to put in. So the answer to that question is I don't have to do anything. There's no data, so there's nothing for head to point to, and since there's no data, there's nothing for tail to point to. So I really don't need this constructor in here at all. Where'd my cursor go? It disappeared. Let's give us some way to add data to this thing. Public void add, and what should the argument for this method be? We don't want it to be linked, and in fact we can't make it be linked because link is private. We want it to be an int. We want the interface to this list to be exactly what someone would expect if they were going to use this list. They want a list to store ints. They don't really care how the list is storing ints, but when they're adding something to the list, they want to add an int. So the parameter for that is an int. We'll call it k. There are a couple of different cases we're going to run into when we're adding things to this linked list. And we'll start with the case that we know we have right now, which is that basically the important part is head points to nothing. So if head equals null, if head equals null, what do we have to do? Well, actually, before we get there, we know regardless of where we're putting this piece of data, we need to store it in a link, right? Link temp equals new link. And just to make link a little bit easier to deal with, let's give it a constructor. It's habit. After I type something, I automatically hit save. Dr. Java doesn't really cooperate with me on that very much. Okay, so the only thing this constructor for link is going to do is save the value I pass it to the data part of the node. So first thing we do when we add it, in terms of adding an int to this linked list, is create a new link with the data that we pass to it. So now, in the case when head is null, we do two things. Just like we did on the board. Head needs to point to this new link, and since we know that it's also the last link in the chain, in the linked list, we know that tail needs to point to it as well. So head equals temp, and tail equals temp. And that's it. Otherwise, so this means this is the case where there are already things in the linked list. Let's not worry about the order, not worry about making sure this linked list is sorted. So this add method will just add the new node to the end, which means we have to do some rearranging of pointers. So we'll start out saying, so tail is at the very end of the list. And we want to add a new node over here. So this node needs to point over here, and then we need to move tail to point to this new node. If we change tail first, we lose access to that last node. Otherwise, we have to go start at head and go all the way through the list. That's tedious. That's time-consuming. We're not going to do that. So the easiest thing to do first out of those two operations is to change the current tail node's next property to point to this new node. So tail.next, and it should point to temp. And then we can change tail to point to temp. Questions? Yes. And if we want to be really efficient about how we write this, we can notice that lines 23 and 18 are exactly the same and put that outside the if statement. And we can be consistent about our conventions as well. So. And at this point, these curly braces look kind of nasty, so clean up the code a little bit. All right. Let's implement a remove method. Who wants to tackle this? You want to tell us how to implement remove? And forgive me, I don't remember your name.
It's Jack.
Jack.
I'm still trying to get past this.
Okay.
Things running a little behind.
Well, just reason through it. Let's start with the easy case. What should remove do if we don't have anything in the linked list? Okay. So now if head does point to something, where should we start? So if head does point to something, we can very easily look at what head points to and see if this is our if this is the element we're looking for. So head dot data. If head.data is equal to k, that means we want to remove the node that head points to. Which means that we have to do a couple things. No, we don't. We only need to do one thing. Java's garbage collector will do the rest for us. Head equals head.next. Okay. Now, what if head does not equal k, or head's data does not equal k, but head's next data is equal to k? Kind of confusing syntax there, but does everybody see what that's doing? I'm looking for head, I'm getting head, which is this element here. I'm then looking at the next element after head, and then looking at its data. So in the illustration on the board, this would be 4. So that ends up being the second node. If that's the case, then head.next should end up pointing to head.next. Right? Does that make sense?
This is the way that you implement it to go in series together.
Right.
So we just have one more data to look for in series.
So at this point, if we kept going with that, we'd get a bunch of head.next.next.next.next.next.data. That would be beyond confusing. This is confusing enough, and also we'd have to implement one of those for every element in this linked list. Since we don't know how long this linked list is, certainly not when we're writing the code, we can't really do it that way. However, this lends itself very well to a loop. So we'll do that. We'll start at the head. While this will be a compound comparison here. So, well, cur does not equal null. So, if cur is pointing to null, that means we reached the end of the list. Whatever we're removing hasn't been found, so we should still stop looping. Otherwise, we'll try accessing a null pointer, and that's bad. And cur.data does not equal what we're looking for. Because as soon as we find it, actually, I don't think I want to put that there. So while cur does not equal null, we're going to continue looping through this, basically going node by node all the way to the end. And we have you could just as easily write this as a for loop, because we still have three pieces. We have an initialization a condition and an approach. Our approach is going to be that cur equals cur.next. So that'll advance cur to the next node. So now we want to check to see if the data on the current node is the one we're trying to remove. So if cur.data is I apologize for my braces. They should be up there. Okay. If we found the node that we're looking for, then we need to do essentially what we've been doing here. So cur.next. No. Cur is the one we're trying to remove, correct? So we need Is that going to work? No. Actually, head is a special case. So if the head node is the one we're trying to remove, that's still a special case, so we need that. And at this point, if we've already removed it, let's return. So we can actually start the current node that we're looking at, that we're inspecting, can start out at head.next. So this second node, and then we can go from there. If the second node is the one that we need to remove, we want to change last, which is head. We want to change head last's next to skip over the node we're removing. No. Last.next equal cur.next. So what that'll do is just skip over cur. Cur won't be pointed to by anything anymore. And at this point, we've removed the thing we're looking for, so we can return. And we can get rid of that. This bit of code is making one very important assumption, and that is that whenever we're removing an int, we only want to remove one instance of the int. So if the int is in the linked list multiple times, we just remove the first one. If we don't want that to be the whoa, how did I get that character in there? If we don't want that to be the case, oh, I know how I got that character in there, like that. Tried to save and hit the wrong character. There we go. We didn't want, if we wanted to remove all instances of k, we would not return there, and we would not return there. We would execute this to cover if head is something we should remove, and then we would cover this loop to make sure that anything else that was that value got removed as well. Questions? Let's implement an index of method. Which will actually be remarkably similar to the remove method. Can start out with the same test. If head equals null, we can return -1. -1 is usually the indicator in things that search for a specific item in a set of elements to represent the item is not contained in the list. If you're searching for a string, a character in a string, and it's not there, it returns -1. It also returns -1 if you give it the empty string and try to search for any character. So for our uses, if this linked list is empty and we try to search for something, let's return -1. And we also have the exact same other special case, the head. So if head data equals k, we're going with 0 index now. So even though this is the first element, it's element with index 0. And then from that point, we can do basically the same thing. That's not a method. Same thing that we do for remove. Start with the, actually, in this case, head isn't a special case, because we're not changing any pointers. So we can get rid of that. We can start with, let's say, int idx equals 0. Idx is a common convention to represent index. And then while cur does not equal null, at this point you should be picking up on some repeated bits of code, kind of trends that are used in traversing linked lists. It's a lot of while the one I'm looking at isn't null, and at the end of the loop, let's go to the next one. So cur equals cur dot next. And now we can say if cur dot data equals k, return idx. And that means that right now, no matter where we find the index that we're looking for, idx will always be 0, which is not right. So every time we go through this while loop, we should also increment idx. Now what happens when we get to the end of the linked list and we haven't found this element that we're looking for? That means it's not in the list. And we already said we'll return -1 for that. So we can just say return -1. Any questions on index of? Similarly, we can write a contains method, which is Boolean and contains. So if head equals null, what should we return? This is probably the easiest question in the semester. False. Yes. Okay. Now we can do something similar to what we had an index of. We don't care what the index is. Hang on. I screwed that up. Okay, we start at head. Likewise, here we start at head. Start at the first node. If that node is the one that we're looking for, we return true. If not, we move on to the next one. If that's the one we're looking for, we return true. We keep doing that until we find the one we're looking for. And then if we get through the entire list, it's not there, we return false. So let's write that in code. While cur does not equal null. If cur.data equals k, return true. Cur equals cur.next. And if we get all the way to the end, again, return false. Any questions on that? Now let's go from the opposite direction, and instead of asking the linked list if it contains a particular element, let's ask the list to give us a particular indexed element. So, kind of like pretending it's an array. So this should return an int. It should get that particular index. We'll call it get. And we'll pass it an index. So now instead of looping until the current element points to a null, we want to loop index times. And each time we should advance to the next one. So we do need, we shouldn't call this cur, we should call it something else. Target. Call it target. Start at head. And this is 0 indexed. So if IDX is, let's say 3. So that means it should point here when we're done. We should get 7 back. If we start at head, we need to advance 1, 2, 3 times. So the same number of times as the index. So while, no, let's do this with a for loop. Right, because we need to loop the same number of times as our index is. If our index is 3, we need to advance 3 places. If our index is 0, we don't need to advance any places at all. And that means that we need to do our advance by one code, which is target equals target.next. At this point, target points to the node that we want to pull the data from. And all that remains to do is return target.data. Return target.data. Target.data. Questions about that? You have a confused look on your face, yeah. Oh, yes, I did. I have issues spelling target. Okay, what am I? Yeah. I have issues spelling period. Alright. I think that's sufficient for data structure in order to test it, right? Let's implement a toString method so that we can actually print out what's going on here. So public string toString. Let's stay consistent. If head equals null, return null. Null is a valid string. It is when it's passed the system.out.println, it will end up printing. I think it's null in parentheses is what it prints out, but it basically indicates that there's nothing there. Otherwise, we should start with a do that, and while cur does not equal null, cur equals cur.next. What's going on here? I'm going to pretend I have a string called str, and I'll declare that in a minute. Str plus equals, let's say, cur.data just a space, not a new one. So now we need string str. It'll complain if I don't give it an initial value, and return str. Make sense for a simple toString? So now let's public class linked list test public static void name string args. I always miss that capital S. That's an A, that's an S. Alright. Linked list LL equals new linked list. add 4. Let's start by printing it out. Not going to be very interesting, but add 4, add 17, shout out numbers.
43.
Good choice. And I'll also add 6 and 9. I'll print it out. And then let's remove 12. It's not in there, so it shouldn't do anything. Let's remove something that is in there, 42. Let's print it out again. System.out.println. Let's also print out the 4th element and contains let's say 9. Test a boundary case. That should be the last one. And what's the last method that we implemented? Used get, used toString, used contains, index of? Yeah. 23. I love it when things compile on the first try. Okay, run. And I don't like it when things crash. So, no pointer exception in get. What am I trying to get? I'm trying to get 4. Well, it's break time at the moment, so in 10 minutes we'll come back and figure out where I screwed up.